Hello everyone, my name is Stephen Hassambelli and today I'll be doing part one of the Ansys Fluent analysis for project one in fundamentals of aerodynamics. So we get started by creating a new fluid flow fluent project here. We right click on geometry, new design modeler. There we go. And we can choose to click the Z axis here, so we're on the XY plane. And once we click XY plane, we can create a new sketch. Click the sketching tab, click rectangle. There we go. Once we do that, we click on dimensions. This is going to be 1.5 meters. And the height will be 0.0, 0.01, which is 10 millimeters. We go. Once we do that, we can click on concepts, surfaces from sketches, click sketch one, hit apply, and lastly, generate. There we go. And now we can exit out of Design Modeler and proceed with the meshing phase. All right, there we go. And right from the get-go, I like to name my selections. And if you want, you can click N to open up this menu as a shortcut, and we're going to name it inlet. This is going to be our moving wall. Outlet, and lastly, fluid. There we go. And here we can see all of our name selections, which will be imported later on into the next steps. And click on mesh. And for the element size, what I have found works best, let me see, it's 5e to the negative 4. There we go. And then we're going to click on generate. This might take a couple of minutes, depending on your PC's capabilities. There we go. And once we have our mesh generated, we can simply exit out of this. And up here, we can click on update so we can update the mesh. There we go. Once that's done, we click on setup. Click double precision, and for people not having the full version, I think you might be limited to 4 processors, but I can put in more than that. I'm gonna wait a little bit for it to load up properly. There we go. Okay, so under models, we want to make sure we change this, and we're gonna select laminar. Okay. Up here on boundary conditions, we can see that all of our previously named selections got imported. And we're going to start by clicking on velocity inlet. And we're going to put in a velocity magnitude of 5 meters per second. On outlet, we're going to click that and just hit prevent reverse flow. It should be good. For the stationary wall, we're just going to open it up and make sure that everything looks correct, that there's no slip, and that it is a stationary wall. And for the moving wall, we're going to click on moving wall here, make sure that the direction is the positive X, and the speed up here will be 3 meters per second. And now on materials, we can change our values up here, either the density or the viscosity, just to achieve a proper Reynolds number. I found that 6e to the -5 works best for me without having to change the density. I'm going to click on change and create and close this tab. After we do that, we just double click on reference values. This is also very important because a lot of times this will not change. We're going to type in the free stream velocity, which is 5 meters per second. We can double check on methods. On monitors, click on residual. And I like mine to run at 1e to the -6. Go. Okay. Then double click on initialization. I like to have it initialized with a couple more iterations, just to have it start better. I'm going to click on initialize. There we go. Once it says it's done down here, we can actually start running our calculation. And I usually put in at least 500. And then we can start the calculation. Okay. And there it goes. And wait for it to finish loading up. And up here, we can also see that the solution has converged, meaning it did reach the 1e to the negative 6 convergence condition for the continuity equation. Yeah, yeah. Hit on OK, and we can exit out of Fluent. Hmm. There we go. All right, and lastly, we can double click on results to open up CFD post, where we can do all of our post processing. And we can start by plotting in all of our velocity and pressure contours. And we do that by clicking contour up here. Velocity. Go. Location, we can just simply hit symmetry 1. And for the variable, we click on velocity. Number of contours, 200 should be fine. There we go. We can see how our boundary layer here is slowly starting to develop. All right, now we're gonna deselect this one and create a pressure contour. Symmetry one again, pressure, and 200 contours. Okay, and now we can add our velocity vectors. And we can either do that by plotting it throughout the whole fluid. Like this. Change the symbol as well. It's too small. There we go. Or what I also like to do as well is put in a line, which we'll call inlet line. Then we'll do also go. Now repeat the same for the midpoint line. And lastly, and I like to do this one slightly before the end of the plates. Go. All right, and for our velocity vectors, now we can also specify the location for it. And because we also have 100 samples, it'll be more defined as well. Um, yeah, and then we're gonna click on location, inlet line, vertex, and because we have 100 samples, that's why this one will be a lot more defined. There we go, and we have many more samples. Now we do the same for all the other lines as well. Go. And last, go. And now we can take a look at the generated vectors. Here's the midpoint. And if we want to see less vectors, we can always just go back to this one, double click on it, and we can reduce the number of vectors by increasing the reduction factor, or we can change the method to maximum number of points. And since we had 100 samples, 100 will be the maximum. If we just wanted 10, yeah, do that as well. Do we have 10? Okay, yeah, we did. But yeah, we can change the number of vectors we want as well. And here's also the outlet velocity. Okay, so now we can just hide all of these. There we go. And what's up next? Next will be determining the maximum velocity and the height of that. And I like to do that by turning on the midpoint the line, the outlet line. We're going to click on location and click on points. We're going to click on max V point. And on method, select variable maximum, the location, the outlet line, variable velocity. There we go. Let's make it a tiny bit smaller again. There we go. All right, and to get the maximum velocity, we're going to end up using this point we just generated, which will be automatically put at the maximum point of the velocity on this line. We're going to click on New Table. There we go. All right, and in this cell here, we're going to click on Function, CFD Post, max val of velocity U, location, outlet line, click on OK, and this should populate with the value. And on the height, we're going to click on probe, the variable Y, at the location, max V point, and this will tell us our height right here, which we can then use to probe for the pressure gradient in the X direction. Okay, and now for the pressure, we also need to create the charts as well. And create a new chart. Let's see. Chart. And we're gonna hit on data series, inlet, location inlet line for the x-axis. We're gonna click on y-axis. So actually, let's invert them. We're going to make a new data series as well. Midpoint line. And here we can see the velocity profiles, which get plotted on the lines that we created earlier. And we can also see that the midpoint line and the outlet line, the velocity profiles on those lines, they are coincident. They're the same, which means that the flow has already fully developed by the time it reaches the midpoint of our two plates. And now for the last step, it will be the pressure gradient. We'll click on new variable up here. Actually, yes, new variable. Click on OK, don't rename it. And on method, we're going to click on gradient and just leave it on pressure. There we go. And now we can go back to our table viewer to see the heights. And what we'll do is we'll go on this same point here and simply probe, but we're changing this to 6, which was the heights. And this was 0.9. I'm going to click on pressure gradient X, and it's going to output our pressure gradient at that specific location. And if we were to do it at 1.5, the answer would be slightly different, but not at anything before that. So that's why I decided to create this line at 1.49 meters downstream. And that was it.